back. In this video we're just going to continue studying continuity, and we're going to look at how it applies to combinations of functions. So we'll start with a algebraic continuity theorem, which basically is like our algebraic limit theorems we've done already, where we look at sums and products and quotients and that kind of thing. And then we'll look at function composition and see how we get on. So as is becoming the theme, for every new thing we introduce, we have an algebraic theorem to go with it. And these are really useful, as we've seen before, for dealing with combinations of functions. So once we've established that a couple of simple cases, like x and 1, for example, are continuous, then we can use this theorem to, for example, show that polynomials are automatically continuous and all that kind of thing. So let's just run through it really quickly, just to get our heads around what's going on. We have two functions, f and g, and they're continuous at some point c in the domain of the two functions. For convenience, we've set it up so that the two functions have the same domain, and that's not too hard to arrange. Okay, so the first one just says that if we scalar multiply our function by k, then the resulting function is continuous at c also. And then we have the usual sums, products, and quotients are all also continuous at c, with the only little catch being providing the quotient f of x over g of x is actually defined. Okay, so if we've got some zeros going on in g, then that's not going to work. Otherwise, our quotients are continuous also. Now, we're not going to actually prove this because the proof is almost identical to that of the algebraic limit theorem for functions, and so we'll just kind of take that one as read. So why don't we take a look at what we can build from this theorem? Okay, so we're going to look at polynomials and we're going to look at rational functions. Now, rational functions, they are just functions that are fractions with a polynomial on top and on the bottom. Okay, so what we should do first is we should verify that x and 1, or x and k, are both continuous for all x's. So we'll just do x, and you can do a constant in the same way. So consider f of x equals x at x equals a. If we want to show that f of x is continuous, let's just practice doing that. So that would involve, we'll say, set epsilon greater than 0. We seek, so as usual, usually the epsilon delta version is more convenient to show that a particular function is continuous than the sequence characterization, but the sequence one is good for other reasons, which we'll see soon. So we seek delta greater than 0, such that whenever, okay, we're just doing standard template here, whenever the absolute value of x minus a is less than delta, it follows that the absolute value of f of x minus f of a is less than epsilon. Okay, and f of x minus f of a is just equal to x minus a, which is less than epsilon. Okay, now this one is really easy because we actually have the same expression here as we have here, so we can just simply say let delta equal epsilon, and this follows directly. Okay, so that's very nice. So our function f of x equals x is therefore continuous no matter what value of a we choose, so it's continuous for all x. So similarly, you can do the same thing, which we're not going to do. You can do it as an exercise. Similarly, f of x equals 1 is continuous for all x. In the real numbers. Okay, so now, if we want to look at, for example, a polynomial, so let's just take p of x is equal to x cubed minus 2x plus 1, then we can break this up as x times x times x minus 2 times x plus 1. Okay, so here we can use a product. This is continuous, as x is continuous. This is product rule. This here is a scalar multiple. So 2x or minus 2x is also continuous. And then overall, we just have a sum by sum rule. So what follows from these two particular cases, f of x equals x and f of x equals 1, is that in fact all polynomials are continuous for all x in R. So all polynomials are continuous just make some space for all x in R. And similarly, rational functions and these are just polynomial divided by polynomial are continuous for x in R except where the denominator is 0. Okay, so that's quite nice. We can always assume that any polynomial we have is automatically going to be continuous no matter what x, and we can just be done with it. Likewise, for rational functions, the only little trap we have to be aware of is where the denominator is equal to 0. Otherwise, we can assume that these things are nicely continuous as well. Okay, but what about if we take the square root of x squared plus 2x plus 1? We can't actually say anything about this one yet, even though we know that the square root of x is continuous. We did that one as an exercise in a previous video. We know that x squared plus 1, x squared plus 2x plus 1 is continuous. But we haven't yet established that if we compose two continuous functions together, like what we're doing here, we're plugging x squared plus 2x plus 1 into the square root of x, we need to justify whether or not that is also continuous before we can actually make a statement about this. So our next theorem is going to demonstrate that if we compose two continuous functions together, then the result will also be continuous. Right, so here's the theorem. The theorem is composition of continuous functions. So there's a little bit of a setup here just because we have to make sure that our continuous functions are compatible. So we've got f, which takes some set A into R, and we've got another function g, which takes some other domain B into the real numbers, and we just have to make sure that whatever comes out of f is able to be put into g. Okay, that's why we make this statement that f of A is contained within B. Right, so again, we've specified our setup a little bit carefully just to make sure when we make the composition function, g composed with f, that whatever goes into, remember that's just g of f of x, if you can't remember that notation, whatever we put into f, when it comes out, f of x has to be able to be put into g. So we're just making sure that the range f of A is contained within the domain B of g. Okay, now the theorem itself starts here, and it says if f is continuous at c and g is continuous at f of c, then the composition g composed with f is continuous at c also. Remember, when we compose them together, the inputs into this function are going to be the domain of f, because the things go into f first. Okay, let's write down what we need. So proof. I'll write a little bit smaller. We'll choose, again, we'll start with our template. This is our continuity template. Choose epsilon greater than 0. We seek delta greater than 0, such that if absolute value of x minus a is less than delta, remember this is continuity, so we don't need to put the 0 on, then absolute value of our composition, which is going to be g of f of x minus g of f of a, is less than epsilon. Okay, so how are we going to go about doing this? Well, again, it's not actually that tricky, because we can control how big the things are at each step, because we have that both of these functions are continuous. So we're going to first choose a delta 1, such that if absolute value of f of x minus g of x is less than delta 1, then the absolute value of g of f of x minus g of f of a is less than epsilon. Okay, so what I'm doing is I'm setting up the outside part of our composition first. So this is to do with the continuity of g. Okay, so this is by continuity of g. Okay, I can always make g of inputs minus g of point less than epsilon if I choose a sufficiently small delta, and I can always do this because g is continuous. So that is my delta of 1. And now I'm just going to choose my regular delta to make sure that this quantity is actually that small. So now, as f is continuous at a, choose delta, this is the actual delta we're looking for now, such that if absolute value of x minus a is less than delta. Now remember, we should be really saying and x is in the domain a, but we can kind of leave that off with the understanding that that's true. Then the absolute value of f of x minus f of a is less than delta 1. Okay, so now we have a little cascade of inequality statements here. So now we've chosen a delta. Here it is. This is the actual delta that we're looking for, this one. If this is true, this is the input to our composition, then it follows that this part here is true. And if that is true, then it follows that this part here is true. And that's what we're actually after. So we've chosen delta to just chain these two things together. Therefore, and hence, we should write that, and hence absolute value of g of f of x minus g of f of a is less than epsilon as required. Okay, so that wasn't too bad. So now we can compose continuous functions together. So we've done square root as an example already. So if you take that one, you can put anything continuous inside a square root, and you're all good, so long as we make sure we're in the domain of square root, for example. Okay, so that's continuous functions. So now we've got quite a big repertoire of tools that let us establish continuity of quite a few different things. Between composition and the algebraic continuity theorem, we can establish continuity of lots of different functions. The last theorem that I'd like to look at in this video is preservation of boundedness. This one is of a slightly different flavor. Now we have a function that's continuous on a closed interval. Okay, so it's continuous at every point on the interval, including the endpoints, obviously. And the theorem says that if our function is continuous on a closed interval, then its set of values f of I, which is just f of all of the values of the interval put together, is a bounded set also. So you can't have a continuous function that results in something unbounded on a closed interval. Now the best way to attack this one is actually proof by contradiction. So we'll assume f of I is unbounded. That means we can't, so if it were bounded, remember there's some value m such that absolute value f of x is less than m. That's what boundedness means. There exists m such that for all x. Okay, that's what boundedness means. So if we're assuming that f of I is unbounded, it means there is no such m. So our functions, our value of our points, f of the points inside the interval, grows without bound. There are, no matter how high a bound we choose, we can always find a point that has a function value above that. Okay, so we're going to attack this one using nested intervals because that's quite a nice approach. So if we take out, let's just write down an interval here. Here it is. It goes from A to B. Now we're going to take this unboundedness property and we're going to partition it into pieces like we've done in the past. So here's I1. I'm going to choose I2. This will be I2. Let's maybe just go different colors so we can make it clear what's going on. Here's I2. And then I'm going to choose half of that to be I3, and I'll we'll talk about the rule that we choose for choosing the halves in a second. This will be I3, etc. So the way that we're going to choose our half intervals is we're going to make sure that we make an unbounded interval choice each time. Because if our overall f of I is unbounded, then f of half of it, at least one of the two halves, is going to be unbounded also. Okay, so let I1 be the half, so let I1, sorry, be AB. Then we're going to choose I2 to be half I1, such that f of I2 is unbounded. And again, if f of I is unbounded, then at least one of the two halves has to be unbounded. And we're going to make that choice. And choose I3 to be half I2, such that f of I3 is unbounded, and we'll continue in that vein. Okay, so at this point in time, we're constructing a nested set of intervals, and we're making sure that each of the intervals is itself unbounded. Okay, so what we've got here is we have these intervals, and we're going to choose a point in each one. And because they're unbounded, we're going to choose them so that the function values of those points are going to be increasing. So we'll choose x1 to be an I1, such that, and we'll go for a relatively easy way. I1 is unbounded, so I can choose to choose a point such that f of x1 is greater than 1. And then I'll take x2 and I2, and this time I'll make it so that the absolute value of f of x2 is greater than 2. Again, because f of I is unbounded, I can make that as large as I want, so 2 is convenient. x3 to be an I3, such that the absolute value of f of x3 is greater than 3, etc. Then, absolute value of x2 minus x1. Now we're going to look at how far, so let's just draw where they might be on our picture here. So x1, let's say it's here. x2, let's just say it's here. I'm trying to make this as far apart as possible, kind of. x3, let's say it's there, for example. But if you look at how far apart at most these things can be, the furthest apart that x2 and x1 could be is b minus a, right? Now if we look at the difference between x3 and x2, this is less than or equal to b minus a over 2. Okay, because now x3 and x2 are both confined to be within I2, and so the length of I2 is half b minus a, and so we can continue this on, and we have absolute value of xk plus xk minus, let's make it minus xk minus 1, is less than or equal to b minus a over 2 to the power of, what will it be? It must be k minus 2. Okay, so point is, these x terms are getting closer and closer together, and in fact you can see from this that they're a Cauchy sequence. They're stuck between 0 and this sequence here, and they automatically therefore converge. Okay, so there are a number of ways of arguing that x converges. Xk, or xn should we call it, is a Cauchy sequence. And hence converges. To some x in our interval. Okay, the distance between subsequent terms is getting smaller and smaller, therefore it's a Cauchy sequence, and hence it's converging to some value x in our original interval. And now, because f is continuous, it must also follow that the sequence of f of xn should converge also. Okay, but clearly it doesn't, because it's just increasing forever by steps of at least 1. So we have our f of x n is definitely not converging to any value. But this thing is unbounded. And does not converge. And I haven't quite planned out my space very well, so let's just jump up to here to finish our conclusion. This contradicting continuity of f. Okay, so our assumption of unboundedness led to a contradiction, and therefore f of I must be bounded. Okay, that's good. So if we got a continuous function on a closed interval, then we're guaranteed to have a bounded set of output values. It cannot go running off anywhere crazy.